everyone, today we're going to look at cubic graph applications. First we're going to look at the relationship between the derivative, second derivative, and the function itself. Next we're going to look at a question where you have the turning points and you want to find the equation of the graph. And lastly we'll look at two higher level questions where you don't know values in the graph, but you can still decide when the graph is concave up or concave down or increasing or decreasing. This page has a lot of information. It's got information about the function, the derivative, and the second derivative. Let's start with the function. The function is your graph that you're drawing. So, if you have something like f of 2, what that means is it gives the y value when x is 2. However, it's different if you have f of x is 2, because in this case the y value is 2. So in the first one, x is 2, but in the second one, y is 2. Now the important thing when you work out a function often is to find the x-intercepts. So that's where you'd make f of x equal to 0. If you have f of x is positive or bigger than 0, you want to find where the y values are positive, in other words, above the x-axis. If you want something like this, f of x is less than 0, this is where the y values are negative. Now the function for a cubic graph would look something like this. Either it will be increasing, decreasing, or increasing, stopping for a second and continuing increasing, or the other way around. Next, let's look at the derivative. Now the derivative is the instantaneous rate of change. In other words, the instantaneous gradient of the graph. So if you want f dash of 2, this will give you the gradient when x is 2. Or if you have this means the gradient is 2. And the gradient in particular, we're talking about the gradient of f of x. What we often use is we work out when the gradient is 0. In other words, when there's a stationary point. If the derivative is positive, it means that my original graph is increasing. If my derivative is negative, it means my original graph is decreasing. So for example, if I look at this graph, the derivative will be positive here, and the derivative will be negative here. Now for a cubic graph, the shape of my derivative graph would be a parabola, either like that or like that. Lastly, let's look at the second derivative. Now the second derivative is the gradient of the derivative. So it gives, here it says, so if I have f, the derivative, f prime prime of 2, it gives the gradient of the derivative. Here I've got f prime prime x is equal to 2. That means I'm looking at where the gradient of the derivative is 2. Now, if I'm looking at the second derivative equal to 0, that would either mean my derivative has a stationary point or a turning point, or if I go back to the original graph, I will have an inflection point where my graph changes from concave up to concave down. If I've got a positive second derivative, it means my first derivative is increasing, or my original graph is concave up. And alternately, if I have my second derivative is less than 0, I know that my derivative is decreasing, or my original graph is concave down. The first example we're looking at today is where you are given the turning points and you have to find the equation of the function. I'll post a link below about questions where you've given the intercepts and you need to find the function. So let's start. The turning points occur when your derivative is equal to 0. So I can work out the equation of the derivative, and this time I'll have a's and b's in that equation. So my derivative is 3x squared plus 2ax plus b. Now at turning points or at stationary points, my derivative is equal to 0. So let's start with the first point, negative 1 and 0. My derivative at negative 1 will be 0. So let's substitute negative 1 into my derivative formula. So I get 3 times negative 1 squared plus 2a times negative 1 plus b. And I simplify that. Now, since I've got two unknowns, I'm going to need a second equation. So let's use the other turning point. Now, at my other turning point, when x is 1, my derivative is 0. Be careful not to make it 4. You're not looking for the point, you're looking for the derivative. Again, I substitute in and get an equation. Now I can work simultaneously. I'm going to use the elimination method to solve the equation. So I write my two equations underneath each other and subtract and add them together. Now the reason why I'm choosing the elimination method is because I have a minus 2a and a positive 2a. So if I add the two equations together, that 2a will fall away altogether and I'll have a very easy equation to solve. So I get, when I solve that equation, b is equal to negative 3. Now, like usual with simultaneous equations, I can substitute that into either one of my equations and find out what a is. And a in this case is 0. That means what I don't have so far is c, and I can't generate a c from the derivative, but I can from the original formula. So let's take the original formula with the a value and the b value that I know, and then I can substitute either point because both of those full points lie on the original graph. So that's the equation of my formula so far, of g of x. I'm going to substitute negative 1 or 0, or I could have substituted 1 and 4, doesn't matter. And then I can solve for c. And there I find that c is equal to negative 2. With these kind of questions, they often ask them as show that kind of questions, where they'll say something like show that a is 0, b is negative 3, and c is negative 2. You'll still do that exactly the same way as this. The only reason they do it that way is if there are questions that follow on, that you're able to do them even if you made a mistake with your first questions. Now I've put together some follow-up questions from the first question. Since we know what a, b, and c are, I know that the equation of the graph is x cubed minus 3x squared minus 2. Now here I've got, it says, for which values of x will f of x be 0? Now what that means is when is the graph positive? When are the y values positive? And you can see in green I've highlighted where they will be positive. Now what I'm missing is I'm missing the second x-intercept. So I can see where the graph will be positive or 0, but I need the second x-intercept. So I'm setting up my equation, and I know that the one x-intercept is x plus, or is negative 1, which means my factor is x plus 1, and since it's a turning point, I'll say x plus 1 squared. So then I'm going to factorize by inspection to see what's missing, and I can see that the missing value, the missing factor in that equation will be x minus 2, therefore my other x-intercept is going to be 2. That means I can find out when my graph will be positive. So when the f values are positive will be either at negative 1, since they ask when there's 0 as well, or it will be onwards from 2. So I've got x is equal to negative 1, or x is greater than or equal to 2. So question 1.2.1 was asking when my function values are positive. 1.1.2 asks when the derivative values are positive. Now the derivative values are positive when my original graph is increasing, because the derivative values give the rate of change. So I need a positive rate of change, and that positive rate of change will result in an increasing graph. So there in green, I've highlighted where the graph is increasing. For that increasing section, I can then see the x values for that increasing section will be less than negative 1 or greater than the turning point, which is 1. So I can write that out as x is less than negative 1 or x is greater than 1. So I've done 1.2.2. 1.2.3 asks when the second derivative is positive. Now the second derivative is positive when my original graph is concave up. Now for finding concave up, I need the inflection point. Now it looks from my picture that the graph's quite symmetrical and that my inflection point will be at the y-intercept. But let's just double check because that's not guaranteed. So my second derivative, the equation of that will be 6x. And so for that 6x graph, I know that my intercept would be at 0. So I know that for the point of inflection, x will be 0, and so for concave up, x will be greater than 0. The second example we're doing today comes from the Classroom Mathematics textbook. Now in this question, I have no constant values on my graph. I only have variables. However, I can still answer the question. So 2.1, for which values of x will f of x be negative? So I want the y values to be negative. That means everything underneath the x-axis. And you can see at the point B, I can't have a point there because f of x will be 0 and I only want values less than 0. So you can see if I look at the x values, it'll be all the x values that are less than 0 except for the one point where my graph touches 0, which will be C. 2.2 says, when is the derivative negative? Now the derivative is negative when the graph is decreasing. So that will be between the two turning points for this graph. The x values that falls between are c, little c, and lowercase a. So for 2.2, my graph is decreasing between c and a, so x is greater than c but smaller than a. Next question. We want to know when the graph is concave up. Now that will be, in this case, after the inflection point. The x value for the inflection point is lowercase d. So basically, x will be everything larger than lowercase d. 2.4 is a bit of a tough question, but don't let it intimidate you. I want to know when two values multiplied together are greater than 0. Now we know that for two values multiplied together being greater than 0, either both must be positive or both must be negative. So let's first consider both being positive. Now for both being positive, I want my first derivative to be positive, so I want my graph to be increasing. There's two sections where it's increasing. I've highlighted that in green. And I want my graph to be concave up, my second derivative to be positive. Now the position where both of those happen at the same time will be all the x values after a. Now the next thing we need to look at is when are both sections negative? So when is my graph decreasing? In other words, when is my derivative less than 0? That will be between my two turning points. Also, when is my graph concave down? Because that's when the second derivative is negative. Now the overlap for those, for the x values, will be between point B and point C. In other words, lowercase c and lowercase d. So x is greater than lowercase c and smaller than lowercase d. The last question we're going to look at today is one that comes from a final exam paper in 2018. It asks you to draw a cubic function, but you're not given the equation of the cubic function. In the list, it says g of 3 is equal to 0, so I know that there will be an x-intercept when x is 3. It also says that the derivative of x is 3 will give me 0, which means I have a stationary point at x is 3. So I know so far that when x is 3, I have both an x-intercept and a turning point, or a stationary point. Next, I'm given the y-intercept. So I know the y-intercept will be at 27. Now this last bit looks a bit confusing, but let's break it down. So firstly, I'm given a positive second derivative, meaning the graph will be concave up when x is less than 3. And the second part says the graph will be concave down when x is greater than 3. Now, if I have a position on the graph where the graph changes concavity, it means I have an inflection point. So when x is 3, I have an x-intercept, a stationary point, and an inflection point. This means that my graph is not going to have the normal up, down, up kind of shape, but rather something will change at x is 3. So let's put the concavity change in. Concave up first, concave down second. And then I can add in the y-intercept. And that will be my sketch.